Okay, hi kids. Now we'll be going with this EMI revision. So in EMI, basically we'll be learning these things. First of all, we'll be seeing like Faraday's law and Lenz's law, which are like from experiments, right? So yeah, Faraday's law. What does Faraday's law say? Faraday's law says something like this: whenever there is a loop and when there is change in flux happening through the loop, there will be induced EMF. And how to find the direction? It's easy to find the direction using Lenz's law, that is, it will oppose the change, right? So Faraday's law says that thing, but yeah, so flux through the loop is changing. How can it change? Flux is like dot product of magnetic field into area. So either magnetic field can change or area can change or the angle between them can change, right? So if area is changing, what does that mean? So you are increasing the area or decreasing the area. If the angle is changing, you are rotating the area. So in both the cases, in magnetic field, you are moving the coil. So we'll see the reason behind it is going to be motional EMF. So motional EMF will be getting generated when you move a coil in a magnetic field. But if you change the magnetic field, then the reason is some other thing, which is induced electric field. These two are entirely two different reasons, but those two can be clubbed with a simple rule called Faraday's law, right? After that, we will be seeing what does self-inductance mean, what does mutual inductance mean, right? So essentially, this is the chapter. Now we will be going further. So first of all, we will be learning about Faraday's law and Lenz's law. And yeah, so you can see some examples here, which are easy examples. So in this particular question, what is happening? A conducting circular loop is placed in a uniform magnetic field with its plane perpendicular to the field. Somehow the radius of the loop starts shrinking. So in magnetic field, the radius is shrinking, so area is shrinking. So the flux enclosed by the loop is going to change. So when there is a change in flux, there will be induced EMF. How to find that induced EMF? Rate of change of flux, right? So that you can manage. So what is the reason? The reason behind induced EMF here is motional EMF. What about this one? A square loop is rotated in a magnetic field. Here angle is changing. So again, what is the reason? You are moving something in a magnetic field. Again, the induced EMF, the reason behind it is motional EMF, right? And this is the base for alternating current, right? Anyway. So if you want to find the reason how it is happening, motional EMF, this is the easiest example you can figure out, right? So when, yeah, you can go by step questions. You can see that this must have been taught in the class. When there is a conducting rod, obviously we will be taking conducting to understand things, right? Because free electrons can move only in a conductor. So when there is a conducting rod moving, so they are asking what is the average force. So if there is a charge, you need to find the average force. So V bar cross B bar if you take, then suppose positive charges are moving, because it doesn't make much difference when you assume positive charges are moving or negative charges are moving freely, right? But we'll see there is one case where it makes a difference. Only in that case I think it makes a difference. In all the other cases you can assume like positive charges are moving. So if positive charges are free to move, then V bar cross V bar, positive charges will try to go this way. Magnetic field will try to push the positive charges here, negative charges here, right? So because of that, electric field will be induced in this direction, right? Now when these two will be equal, then the movement will stop, kind of, right? So that is the reason behind EMF. What is the reason behind EMF? When you move a conducting material in a magnetic field, because of the magnetic force, there will be induced EMF, right? Because of the magnetic field will be trying to push it, right? So that is providing the required EMF, right? Now, yeah. So motional EMF is the reason behind why there is current flow in Faraday's law when area is, or when you move something when you move the material in a magnetic field, right? So you must have learned all these things, and you can replace. Whenever you see it will behave like pushing the charge, you can replace this one with a battery. Now it's not like you have to replace here. It is like the EMF will be like induced at every point. When you add all this, it will turn out to be this one. So for simplicity, we can put it this one separately and resistance separately. Effectively, this thing effectively behaves like this, but it doesn't mean this is happening exactly here, right? Okay, so after that it looks like a simple circuit. You can use like all the rules of current, electricity, and you can do it, right? Now even you can prove like in two ways. I mean, here you have seen the induced EMF will be of the form V bar cross B bar dot DL bar, but the same thing you can prove it by rate of change of flux by Faraday's law. Anyway, that's fine. I think you must be knowing it anyway. So what we have seen, Faraday's law Yeah, when a loop is moving in a magnetic field, Faraday's law says induced EMF will be d phi by dt. Motional EMF says V bar cross V bar dot dl bar, both will be equal, that you can prove. Now comes the question. If you look at this question, there is a rectangular loop being pulled out of the magnetic field with a uniform velocity by applying external force. The length Mn is equal to L. The length Mn is equal to L, and total resistance of the loop is R. Find the current in the loop. So if you want to find the current in the loop, you need to find the induced EMF. Induced EMF in this one is going to be 0, in this one is going to be 0, in this one is going to be 0. There will be induced EMF only this one. It will be V bar cross B bar. Now by using Faraday's law, you can say what is the induced EMF, but you can't say where the induced EMF is happening. Faraday's law said the total induced EMF in the loop, but the reason, motional EMF, by going with the reason, we can see motional EMF will be getting generated here. So Faraday's law says in the total loop what is the induced EMF, but by knowing the reason, we can find even the location, right? So induced EMF will be here. So how much it will be? V bar cross V bar dot L. So it will try to push the current this way, right? When the current is happening this way, you can see the force on this one will be opposing, right? These two forces will be getting cancelled. Force on this one is going to be opposing. Now you need to apply that much force on this side to move with uniform velocity, right? So that will be your next question. What will be the magnetic force? These two will be getting cancelled. Now average magnetic force, that is, right? Okay. Now if you apply the same amount of magnitude of force, then it will be moving with a constant velocity. Now after that, you need to find what is the power delivered by U. How to find power delivered by U? The force applied by U times of velocity, and they are asking what is the thermal power dissipated in the loop, that is I square R, right? Now when you do that, current you can get, after that you can get the force. This much force is the magnetic force on average, so you need to pull it with same amount of force. So what will be the power by U? Power by U is this much, which will be exactly equal to the power dissipated in the loop. So what they wanted to convey here, they wanted to convey whatever power utilized by the loop, it's coming at the expense of external source. They are trying to stress on the point magnetic force doesn't do work. Though we feel like magnetic force is applied in this direction, it's not actually. Actually, when you go into microscopic level, how it looks, right? Okay, this PDF will be available. If you want, you can check. But if there is some charge here, and if the rod is moving with a velocity, then what will happen? The charge, apart from this velocity, there will be some velocity in this direction also for the charge, right? So effectively the velocity is going to be this direction. If the velocity is going to be this direction, V bar cross V bar, then the force is going to be this direction, right? If the force is going to be this direction, this is the magnetic force, right? Magnetic force is perpendicular to velocity, so it must not do any work. Then who is driving the current? This one. But this guy is applying the force in the horizontal direction. How can he drive the current in the vertical direction, kind of stuff, right? So anyway, if you want to understand, there is analogy here. By analogy you can understand it easily. So what will happen here is, there are two kinds of forces. One is force applied by you, one is magnetic force. Now you are doing positive work, net magnetic force will be doing 0 work. But if you resolve the magnetic field into horizontal component and vertical component, work done by you and work done by this component is going to be cancelled, and work done by this component is going to be positive. So whatever work you are doing, this magnetic field is trying to convert the direction, kind of thing. I mean, we can't say work done and direction, but you can see the analogy. What does the analogy say here? If there is an object here, if you apply, this is fixed wedge. If you apply force in this direction, it will go in the upward direction. Now it is increasing potential energy. You are applying force in horizontal direction, then how is potential energy getting increased? Why is it moving vertically? Work done by this one is 0, right? Because it is moving along this direction and it is perpendicular. So you are applying the force horizontally, but you are increasing the potential energy because of the field in the vertical direction. How is that happening? If you see here, work done by normal is going to be 0, but work done by normals, this component is going to be negative. Work done by normals, this component is going to be positive. So this negative work done is getting cancelled by work done by you, and this positive work done is trying to increase the potential energy. So effectively you are doing work, but what is normal reaction doing? Normal reaction is trying to change the direction, kind of thing, right? So whatever normal is here normal is doing 0 work, but it is diverting the particle's motion, right? So the same thing will happen in magnetic field also. The analogy is this normal will behave like magnetic field. Now that's the same explanation from other book. Anyway, that's not much needed. All you have to understand is magnetic force will never do work because it will always be perpendicular to the velocity. Now you can look at this question. So essentially the question goes like, there are two rods here. So what will be the induced EMF when you move it with a velocity v? So why I have taken this question is, you will be saying effective length. We will see when we can apply effective length and how we can apply effective length, right? So what is the reason behind induced EMF here? It is motional EMF, because you are moving something in a magnetic field. When it is motional EMF, then induced EMF is going to be v bar cross v bar dot dl bar for small element. Then if you integrate, you will be getting for the total element. Now velocity is constant given in the question, magnetic field is constant given in the question, so you can take it out of integration. So integral dl bar, if there is any loop like this, not only that loop. So what is integral dl bar? Integral dl bar is adding all these small vectors, right? So when you add all these small vectors, what you will be getting? You will be getting effectively this vector, right? So L effective. So instead of adding those small induced EMFs, you can directly get the induced EMF for this line. Both must give you the same answer. That's what it says. Now, if at all it is a full closed loop, L effective would have been 0. Induced EMF in a closed loop is 0. Faraday's law says the same thing. Even motional EMF also says the same thing, right? So what you can do from next time, when there is a uniform magnetic field and velocity is also constant at that particular time, then instead of this entire loop, you can replace with a effective length, right? Or the other way of saying it is, the induced EMF when you go from here to here and here to here must be same, because in the total it has to be 0, right? So if here to here it is same, here to here it is same, when you go in a loop it is going to be 0, right? So that is how we will be applying effective length thing. Now this is the place where you need to understand, if you visualize current as positive charged particles, and if you visualize the current as motion of negative charged particles, it makes a difference only here. In all the other places, I think it doesn't make much difference. So when someone says about Hall effect, be careful about assuming which charges are moving. Better don't assume, right? So anyway, you can do the question by yourself. What I wanted to say here is, if there is current going in this direction, if I assume current flow is because of positive charge movement, if current is in this direction, then the positive charges will be going in this direction. If I assume current is because of positive charge movement, now what will be the force on that positive charge? V bar cross V bar, V bar cross V bar. So this side, top side is going to be accumulated with positive charge and bottom side will be going to accumulate with negative charge. Now if I assume current is because of negative charge movement, if current is in this direction, then the negative charge must flow in this direction. So V bar cross V bar, V bar cross V bar is in this direction, but Q into V bar cross V bar we need to find, it is negative charge, right? V bar cross V bar, but it is negative charge. So negative charges will try to accumulate here and positive charges will accumulate here, right? Now if you see, it makes a difference here. Here if you assume current is because of positive charge movement, upper phase is going to be at higher potential and lower phase is going to be at lower potential. When you assume current is because of negative charge movement, upper phase is going to be lower potential and lower phase is going to be higher potential, right? So when you connect voltmeter, what will happen? Voltmeter will show the upper phase is at higher potential and lower phase is at lower potential. This one, upper phase is at lower potential and lower phase is at higher potential, right? So but in reality what will happen when you do this won't happen. When you connect voltmeter will show upper phase is at lower potential and lower phase is at higher potential. By that you can conclude the charges which are in motion are negative charges. I mean in conductors you know, but if you take some other experiment where you don't know the current is because of positive charge movement or negative charge movement, if you want to find out, then you can use this method, right? And this is called as Hall effect. And see, I have seen kids asking me like, kids telling me motional EMF is nothing but Hall effect. I think there is a difference. So it's better not to use Hall effect. It's better to use motional EMF whenever it comes in syllabus thing, right? Now going to the next part, it is this question. You can see, if a metal disc of radius a rotates with a constant angular velocity, find its potential difference between the center and the rim of the disc. If external magnetic field is absent. If external magnetic field is absent, what will happen? If magnetic field is there, what will happen? So if external magnetic field is absent, when metal disk is rotating, the free electrons must be rotating. I mean, once stability is achieved, right? So steady state is achieved. That electron which is here at a distance r, if it is performing circular motion, there must be some force towards the center. Who will be providing that? That must have happened because of the accumulation of charges. Because of the accumulation of charges, this will become more negative charge, this will become more positive charge kind of thing. Then there will be force on the electron in this direction, which is E into electric field there. Electric field will be in this direction, so force will be in this direction. So net force equal to mass times of acceleration. From here you can see electric field is this much. If you know electric field as a function of distance, then if you want to find the potential difference, then it is going to be this much. It is going to be this much. That you can do, but we don't do it generally. We don't do it generally. We will see why we don't do it generally. When there is no magnetic field also, there will be induced EMF between the center and the end. Now when there is magnetic field, this is a very common question. When there is a magnetic field, there will be induced EMF, but we don't stress that much on induced EMF because of presence of electric field, right? Now suppose if now the same thing with magnetic field is there, then what will happen? Because of magnetic field, let me say it is rotating with omega, so it is electron V bar cross B bar, but it is negative charge, so magnetic force is going to be in this direction. After accumulation of charges, let me say electric force is going to be in this direction, because net force towards the center must become equal to m omega square r. I can write this one. So from here I will be getting electric field as a function of r. So when I do the integration, I will be getting this one. But generally when we do, we won't be considering this term, we won't be considering this term, we won't be considering this term, right? So sorry, not this one. Yes. So why we won't be doing that? Why will be neglecting this electric field thing? Because you can see when it comes to real life, the values are going to be, this is going to be 3 nanovolt and this is going to be 20 millivolt. This is very high and this is very small, right? This is very small. So compared to this one, this is going to be very small, so we can neglect its effect in real life when we do those questions, right? Anyway. And what is the reason here? Obviously you are moving conductor in a magnetic field, so the reason is motional EMF. By Faraday's law, you won't be getting much clarity over this question. You can get clarity only using motional EMF, right? So what we have seen, Faraday's law we have seen, and we have seen the reason motional EMF. When will motional EMF come into picture? When you move a loop in a magnetic field. Now if you look at this question, here loop is not moving in the magnetic field, current is increasing continuously. If the current is increasing continuously, what will happen? Magnetic field here is increasing continuously, so flux is increasing continuously. If flux is increasing continuously, then induced current will try to oppose the flux, right? So induced current will be in anti-clockwise direction. Right? So what is the reason here? Here loop is not moving in a magnetic field, so it is not going to be motional EMF. So but when they try to figure out what is the reason, what they got it, obviously loop is not moving, but still there is induced EMF. If loop is not moving, there can't be magnetic force, there must be only electric force. From there they concluded if there is change in magnetic field, it will create electric field, and that electric field is going to be induced electric field, which is non-conservative in nature. And generally this is the most commonly asked symmetrical question, because only in this particular case we can figure out how the field lines are going to be. When a uniform magnetic field exists in a cylindrical region as shown in dotted lines, and it is increasing at a constant rate. So if magnetic field is increasing at a constant rate, there will be induced electric field in the opposite direction, right, in anti-clockwise direction, and there will be the electric field lines will be concentric circles. You can say the electric field lines will be concentric circles only in this particular cylindrical kind of region. In all the other cases you can say Faraday's law, but you can't predict the field lines direction properly, right? Now the most commonly asked question is, what is the induced electric field inside when it is at a distance r? What is the induced electric field outside when it is at a distance r? These are two very basic questions what you need to know. So let us do one thing. If there is this magnetic field and which is increasing in this direction, then there will be induced electric field in this direction. If I want to find electric field at a distance E, at a distance r, then what I will be doing, I will be doing with induced EMF in this circular loop is rate of change of flux, which is Faraday's law, right? So induced EMF in the loop integral E bar dot dl bar is equal to rate of change of flux. This is Faraday's law. Now how to find rate of change of flux? Yeah, flux is magnetic field there times area enclosed. Magnetic field there times area enclosed. What is the area enclosed? Pi into small r square. Pi into small r square. You can take this one as capital R, but this capital R is not the flux enclosed. What is the flux enclosed? Pi into small r square. Right? Now here I have done something. E bar dot dl bar is nothing but E into dl I have done. That I can do only in this particular case because electric field is tangential, which is along the direction of dl. Now I can even take electric field out of the integration because by symmetry I can say electric field magnitude will be same at every point. Now what is integral dl? Integral is dl is going to be 2 pi r. Now on the right hand side this is a constant, so dv by dt, right? So from here you will be getting electric field is r by 2 into dv by dt. This is electric field induced inside when there is a time varying magnetic field. Now similarly, if you want to find what is the electric field induced outside, if this is the time varying magnetic field, if you want to find what is the electric field outside, again you will be going with the same Faraday's law. Again these two will be in the same direction and E is same at every point, so you can take it out of integration. Integral dl is going to be 2 pi r. On the right hand side, flux enclosed. Now this is capital R, this is small r. So even though this total area is pi into small r square, flux enclosed is only in this region. So area is going to be only pi capital R square. Only pi capital R square. Now from there you will be getting electric field when the point is outside, right? So these two are very commonly asked things, so you must be aware of how to do them. Now you can solve the next question. This is from H.C. Verma, so he asked something to show. Consider a point P and you need to show field along that direction is going to be same. The other way of saying it is, if you take some other point here, if you take a square and here we found the electric field, and if you find electric field here, that is going to be in this direction, but when you take its component, he is asking you to show this electric field component is going to be same as this electric field. So that even we have seen when it is at a distance r, we got r by 2 into dB by dt. Similarly, we can show when it is at a distance x, it is going to be x by 2 into dB by dt. But what you need its component. If this is theta, then this angle is 90 minus theta, this is going to be theta, so E1 cos theta. E1 cos theta. E1 cos theta is x cos theta by 2 into dB by dt. What is x cos theta from the figure? It is r. R by 2 into dB by dt. R by 2 into dB by dt is nothing but the same thing what we got here, right? Which is nothing but electric field here. Anyway, that doesn't matter much. But you need to be aware of how to do this, how to find the electric field inside and outside. Right, so now there is a uniform magnetic field perpendicular to the plane of the figure in circular region of radius A centered at O. ABCD is a conducting loop in the plane with its arms BC and DA along two radial lines. BC and DA along two radial lines. From O having an angle theta. AB is a circular arc of radius OB equal to D centered at O, and CD is a circular arc with radius B. So magnetic field is changing at a rate dV by dt. So you can take it like increasing or decreasing. We'll see what I have done. Find the induced EMF in the loop ABCD. ABCD. So if you take this loop, what is the flux enclosed? Flux enclosed is 0. Because magnetic field is here, flux enclosed is 0. What is the rate of change of flux? Every time it is 0 only. So what is the induced EMF? Induced EMF in the loop is going to be 0. In the loop it is going to be 0. But when you talk about EMF induced in the arc AB, let us see how to find what is the induced EMF in the arc AB. When there is, okay, let me see what I have done. I think I didn't do anything. So let us assume something. Let us assume magnetic field is increasing. If the magnetic field is increasing, then the induced electric field will be going to be in this direction. So concentric circles, induced electric field lines will be concentric circles. Now if I want to find E bar dot dl bar for this one, so I need to find what is the electric field there, and I need to take the dot product, but or we can make it in the easier way. Instead of finding the electric field there and finding the dot product, I can go by the other way. That is, I can make a closed loop here. If I make a closed loop here, these are radial lines. Electric field lines are concentric circles, so they will always be perpendicular to the radial line. So induced EMF along radial line is going to be 0. Induced EMF along radial line is going to be 0. So radial lines will always help us because induced EMF along the radial lines is going to be 0. So, but you know this is a closed loop, this is a closed loop and it encloses some magnetic flux. So what is that magnetic flux? It is magnetic field there into theta into a square by 2. This area is a square theta by 2, right? So this is area, this is rate of change of magnetic field. What does this give you? This give you rate of change of magnetic flux. So what is the total induced EMF? Total induced EMF is rate of change of magnetic flux, but in this one it is 0, in this one it is 0. So whatever induced EMF happens in this loop, it is going to happen here, right? Now what about the direction? If magnetic field is increasing, then the induced EMF is going to push it in this direction, right? In this direction. Now similarly, if you want, you can prove for this one also. Now again I will be taking radial line, area enclosed is still same, flux enclosed is still same, and EMF induced is 0 in this one, So I can easily show EMF induced in this one is going to be this much, which is same as magnitude of induced EMF for this one. Now when you make a closed loop, induced EMF in this one is going to be this direction, in this one is going to be this direction, right? So when you look at this as a total loop, this electromotive force and this electromotive force is going to cancel, right? So what is the total induced EMF? Total induced EMF is 0. That you can predict by Faraday's law, but if you want to look from the reason point of view, there is a induced EMF in this arc because of induced electric field. There is EMF in this one also because of induced electric field, but their summation is going to be 0. And radial lines will help, be aware of it. Now going to the next question, a uniform magnetic field B exists in a circular region of radius r. The field is perpendicular to the plane and is increasing at a constant rate. There is a straight conducting rod AB of length 2r. Find the EMF induced in the rod when it is placed as shown in the figure. Point C is the midpoint. So what about this? When there is a time varying magnetic field and it is increasing, they said, so induced electric field will be concentric circles. Induced electric field will be concentric circles. This is a radial line, so EMF induced is always 0 because electric field is going to be perpendicular. So what is the induced EMF for this rod? It is going to be 0. But what about this one? Induced electric field, it is not perpendicular, it is making some angles. So I don't know, but I can find electric field there and take the component, take the dot product, but we'll try to avoid it. We'll try to use Faraday's law. So what I can do, I can use two radial lines and I can make a closed loop, right? I can do it in many ways. I can say, I can see a square. So if induced EMF in this one is E, then in this one also is E, and this one also is E, in this one also is E. So if I can find what is the induced EMF for total square, I can say induced EMF in this one is 1/4 of that, right? So induced EMF in CA is nothing but whatever happens for 1/4 of whatever happens for this square. So what will happen for the square? It is dB by dt into flux enclosed, right? Now flux is enclosed only for this region, so which is pi r square, right? So which will be dB by dt is given as alpha in the question. So that way you can get, or we can get it by this way. This is more general way. What we do is we'll take this closed loop. We can, that they have done. You can see here, I think that's the reason I didn't do it. You can take a closed loop like this. So induced EMF in this total closed loop is going to be rate of change of flux through this area. Now what is the flux enclosed? Flux enclosed is this circular area, sector area into rate of change, into magnetic field. That is the flux. Now if you want to find rate of change of flux, you can do that. But induced EMF in the radial line is going to be 0, in the radial line is going to be 0. That is the important thing. So whatever induced EMF happens for this closed loop will happen along this line. That is going to be, that you can calculate 1/4 of, right? Now the other way of getting it is this one. What we have seen how to get it like a square. We have seen how to get it like a sector. Now I am going to take a closed loop like this. One is this and one is this. Now I can find E bar dot dl bar for this curve easily. That is, you can do it as homework, or we have seen it earlier also. So, but if I take this full loop, there is no flux enclosed. So there is no rate of change of flux enclosed. So there won't be any induced EMF. So whatever induced EMF happens for this one, the same thing must happen for this one. So that when you go in a loop, it has to be 0. right? So the same thing will happen here also. Whatever it is, you can choose your method. Now we will go for the other part. If AB is a conductor, then what is the induced EMF? What is the induced EMF? We got it as pi r square by 4 into alpha. Now what is that pushing force direction? It is like magnetic field is increasing, so induced electric field will try to push the positive charges this direction, right? Now if I talk about this particular point, then non-conservative electric field is going to be perpendicular, right? So it is concentric circle, right? So if I draw some imaginary line, then the induced electric field, which is non-conservative, is perpendicular to that line. Now if there is free electron, it won't be moving, right? Because after some time the charges will be like settled, right? No current flow will happen, right? Because it is open. How no current flow is happening when there is non-conservative electric field here? Because of the accumulation of charges, there will be conservative electric field happening in the opposite direction. So these two will be exactly cancelling. So even if there is free electron there, it won't be moving. So conservative electric field developed because of accumulation of charges. Now you can see there will be more positive charges accumulated here and negative here, something like that, so that you will be having electric field component in this direction, conservative electric field component in this direction. And potential difference is always defined for conservative forces. So whenever someone talks about potential difference, you need to bother about field because of conservative forces, right? So electric field is in this direction, so this is higher potential and this is lower potential. Conservative electric field is in this direction, so this is higher potential and this is lower potential. The other way of saying it is positive charges are going to accumulate here, negative charges are going to accumulate here, something like that. So you can see this is higher potential, this is lower potential, right? So VM minus VB is how much? The same thing. I mean, because when you do this non-conservative DL integration or conservative DL integration, magnitude wise they have to be same. Now suppose if you connect a voltmeter, to measure what is that potential difference. What was that potential difference? Pi r square by 4 into alpha we got. Now if you connect a voltmeter what it will be having? It will be having some resistance. Now apart from that, just now we have seen this total loop, there is no flux enclosed, so the total EMF induced has to be 0. How that can happen? Whatever induced EMF here must be same as induced EMF here. Now this entire thing will have some induced EMF which I have placed here. I mean, I need to place part by part, but you can understand, like for this entire rod it is going to be E and this entire resistance is R. Now voltmeter will have some resistance, very high resistance, and yeah, this induced EMF for this line also. So if I write loop equation, what it is going to be? It is going to be plus E minus IR minus I into voltmeter resistance. This V represents voltmeter resistance, minus E equal to 0. From there I can see I equal to 0. So what will voltmeter read? Voltmeter will read what is I into V reading, right? That is I into V is nothing but integral, finding potential difference using that integral form, whatever. I into R is going to be how much? 0. So the reading is going to be 0. If you don't connect voltmeter, the potential difference is going to be pi r square by 4 into alpha, but when you try to measure it, it will turn out to be 0. Now similarly, if you take a non-conductor, that is if the electrons can't move freely, even though there is non-conservative electric field, the free electrons, I mean there won't be free electrons, so the charges won't be moving, there won't be any accumulation of charges, so there won't be any non-conservative field developed. So there is no potential difference between A and B, but there will be induced EMF. Induced EMF will always be there, there will be always pushing force in this direction, but they won't be moving because of those internal bondings. Now if you connect a voltmeter, what will happen? Still, because of the bonding, electrons are not able to move, so there is no current flow, so voltmeter won't be detecting anything, so the reading is going to be 0. Now if there is no material, if I am just talking about those 2 points in space, still there will be induced EMF, because induced EMF doesn't depend on whether material is there or not, right? So there will be induced EMF which is this much, but there will be no potential difference, because there is no material, there are no electrons which can flow and which can create conservative electric field. And if you connect voltmeter, obviously it is open circuit, no current will be flowing through that, so reading is going to be 0. Now you can take this as homework, you can do it much easily. They have done something and you can see it, like if you want to find induced EMF along this line, you can see it like as a triangle where this angle is going to be pi by 2, and induced EMF along the radial line is 0, along this radial line 0. Induced EMF is along this line is going to be same as induced EMF for this total loop, which will be given by dB by dt into this area enclosed. Now this one also you can do by yourself. There will be, induced EMF in one loop will try to rotate in one direction, will try to produce current in one direction. Induced EMF in the other loop will try to produce the current in this in other direction, but whichever will be more, that will be trying to dominate, right? So this one minus this one you will be getting. Now there is this question: a square loop of side 12 cm with its sides parallel to x-axis and y-axis move with a velocity in positive direction in the environment containing magnetic field in positive z direction. The field is neither uniform in space nor constant in time. Okay, so there is time varying magnetic field, and at the same time it depends on the distance also. It has a gradient along negative x direction, that is it increases as it moves along negative x direction, and it decreases in time. Determine the direction and magnitude of, okay, anyway, you can see the given solution. This is from NCERT. Now if you want to do it, then this is how generally I do it. Here it is combination of both. Here loop is moving in a magnetic field, at the same time magnetic field is varying with time. So there will be motional EMF, there will be induced electric field, because loop is moving in a magnetic field. When loop is moving in a magnetic field, there will be motional EMF, and especially it is not uniform magnetic field, right? So in a non-uniform magnetic field, when you are moving, there will be motional EMF. The other thing is magnetic field is varying with time. When magnetic field is varying with time, there will be induced electric field, right? Now there are both reasons. Two reasons are different, but we know we can combine them using single law called Faraday's law. So I will be taking help of Faraday's law. Now what I am doing is at any time, when I take a picture at any time, it looks like this. Magnetic field here I assume it as B. Magnetic field varies with distance along x-axis this side. So at x equal to 0, I assumed it as B. So what is the magnetic field here? According to the given question, it is B minus 10 power minus 3 into x. 10 power minus 3 per centimeter into, right? So generally it has to be B minus 10 power minus 3 into x, but if you want to write it in mathematical form, it is B plus dou B by dou x into x. So what is the flux through this one? Flux through this one is going to be this much, and when you integrate it from x1 to x1 plus a, you will be getting total flux enclosed is this much. Now you need to find what is the rate of change of flux. So for that, what you need to do, you need to differentiate both sides with respect to time. When you do that, you will be getting this much. Now this component is coming because of time varying magnetic field. This component is coming because of moving a loop in a magnetic field. Or this component, the reason behind this component is motional EMF. The reason behind this component is going to be induced electric field. So whenever both come together, it's always better to use Faraday's law, because Faraday's law clubs two unique things as some easy law, right? Now, I mean, you must have seen these questions earlier. So if there is a conducting strip displaced with a velocity v through a magnetic field applied in the figure, whatever. So there is a magnetic field here, there is a conducting strip which is moving. So will there be deflection in the galvanometer or not? This is the question. Magnetic field is applied, okay, it is outward direction, say. Now, by going with Faraday's law, you can't easily understand like what is the flux and stuff, all those things. But if you go with the reason, if there is induced EMF here, that could be only because of motional EMF, because magnetic field is not varying with time. So the reason could be only motional EMF. So let us look from motional EMF point of view. If there is motional EMF, if I take this strip, so that is moving the velocity v, so v bar cross b bar. If we assume positive charges movement, then positive charges will try to go this way. So there will be current, v bar is in outer direction, right? So v bar cross b bar, so positive charges will try to go this way. If positive charges are trying to go this way, then the current is flowing in this direction, right? So there will be a flow of current in the galvanometer. You can't find it exactly using Faraday's law, but you can give motional EMF reasoning to understand it better. Now in the same way, if you see here, there is a galvanometer here, there are two wires which are initially connected here. There is a there is a magnetic field here which is constant, which is not time varying. Now there is a ring here, you are moving the galvanometer over this ring, and they are asking will there be any deflection in the galvanometer. Again here magnetic field is not varying with time, so if there is any reason, that must be only because of motional EMF. When will motional EMF will get generated? When when the conducting material moves in a magnetic field, when conducting material moves in a magnetic field, then the free electrons will be experiencing some force. But here you are moving the conducting material out of the magnetic field, so there is no way force can be applied on electrons by magnetic field, right? So motional EMF won't be there. Even though you can see initial flux enclosed is 0, final flux enclosed is not 0, still there is no EMF induced because there is no reason, right? Now this question also goes the same way. Initially if it is like this, finally when you open it, you may feel like the flux enclosed initially is only this much. When you open it, the flux enclosed is this much, but again it's essentially the same question as our earlier one. Here it is magnetic field is uniform, so motional EMF only can be induced. Motional EMF can be induced only when material is moving in magnetic field. Material is not moving in magnetic field, it is out of magnetic field, so there won't be any motional EMF, right? So you need to know the reasons to understand things better. Faraday's law came out of experiments, but maybe he didn't find that fault in his experiments because he might have never tried this kind of thing. The next question goes like, an EMF induced is produced in a coil which is not connected to an external voltage source. This can be due to coil being in time varying magnetic field. Yes. So what is the reason? If a coil is in a time varying magnetic field, EMF will be because of induced electric field, which is non-conservative. Then the coil moving in a time varying magnetic field. If the coil is moving in a time varying magnetic field, so there is a chance of motional EMF, there is a chance of induced electric field also. So the reason could be both. The third one, the coil moving in a constant magnetic field. So when a coil is moving in a constant magnetic field, still you can change the flux enclosed through that by Faraday's law if you want to see. Now if you want to see by motional EMF also, you can see the very first example what we have seen, where heat is getting generated, where you are pulling the loop out of the magnetic field. There by motional EMF also you can explain, by Faraday's law also you can explain. So when a coil is moving in a constant magnetic field, the reason is motional EMF. What about the last one? The coil is stationary in external spatially varying magnetic field but does not change with time. So there is magnetic field whose value is something at origin, whose value is something at x equal to 1, whose value is something at x equal to 2, but it is not changing with time. So let me say if it is 1 millitesla at origin, so it is 1 millitesla at origin forever. So if it is 2 millitesla at x equal to 1, then it is 2 millitesla forever. So it is varying only with space. Now anyway the loop is not moving. The magnetic field is not varying with time, so there is no induced electric field. The loop is not moving. When the loop is not moving, there is no velocity for average velocity, so there won't be any motional EMF also, right? The next question, an aircraft is flying at a level height in the presence of magnetic field of Earth. If an electric bulb is connected between two extreme ends of the wings, then will there be voltage induced and will the bulb glow? So this is the kind of question they are asking. So if I visualize it this way in a easier way, so if there is a plane aircraft which is moving in this direction with a velocity v, for simplicity I have taken magnetic field is into, that doesn't matter, you can take the magnetic field in any random direction also. Now there is bulb, will this glow or not? Will there be induced EMF along these two ends or not? That's the question. So what we can do here is, I can try to put equivalent circuit. So this entire thing will behave like some EMF source, V bar cross B bar, so BLV, right? Anyway, I am calling it as E. So and we can put something as resistance, So just follow what I am saying, because okay, the first thing is this one I know. I just replaced this entire part with a EMF and a resistance. Though I know it must be like I can't put it together, but I know for this entire rod it is going to be EMF is E, for resistance is R. Now for this loop also EMF has to be E. That you can go by effective length or you can go by total loop. Flux in the total loop is not changing, so total EMF induced has to be 0. So when you go in a loop, total EMF has to be 0. Now apart from that, bulb will have some resistance, so I have put it here. Now you can see when you go in a loop, net EMF is going to be 0. When net EMF is 0, then the current is going to be 0. When the current is going to be 0, bulb won't be glowing. But when current is 0, if I assume this potential as 0, this potential is going to be E, this potential is going to be E. There is a potential difference of E, whether you go this way or this way. But when you go in a loop, the net potential is going to be, the net EMF is going to be 0, right? So there is a potential difference. There is a potential difference. These two are same potential because no current is flowing through the resistor, right? So there is a potential difference, but there won't be any current flowing in the bulb. There won't be, bulb won't be glowing, right? No voltage will induce across, a voltage will induce across the wings. A voltage will induce across the wings, but bulb will not glow. There is a voltage induced across the wings, but bulb is not going to glow. Now similarly, going to the next question, in a cylindrical region that is encircled by a uniform metallic ring, a uniform magnetic field perpendicular to the plane, rings varies in time in such a manner that constant EMF of 12 volt is induced in the ring. A voltmeter of very high resistance is used to measure potential difference between 2 points of the ring separated by 1/4 of the ring. 1/4 of the ring, this is quarter. But you are joining a voltmeter in one way in first case, in the other way in the second case. So you need to find how much it will read in both the cases. How much it will read in the both the cases. So what I am going to do is I am going to see what is happening without voltmeter. If there is no voltmeter, so what I have taken, magnetic field is into and it is increasing. If magnetic field is increasing, then the induced EMF, induced electric field will be trying to push the current in this direction. So for this entire loop, there will be induced EMF, which I have put it here. For this entire loop, there will be some resistance which I have put here. But over a loop, KVL has to be valid, right? So plus E minus I into R equal to 0. So I will be getting E equal to IR. Now I am looking at the first case. If the voltmeter is connected here, what I can see is voltmeter has very high resistance, so the current flowing in this line has to be very small. So current in this one and in this one will be almost same as the earlier one. Out of this only, it will change only partially, so I am taking like approximately same as the earlier one. Now for this loop, induced EMF is going to be 1/4 and resistance is 1/4. Because we know it is equally spread, right? That EMF is going to equally spread and resistance is going to be equally spread. So this much I can do. Now for this one it is 3E/4 and 3R/4 I can do. Now if you look at this part, the total flux enclosed is 0. So the total EMF has to be 0. If the total EMF has to be 0, how it can be? If this is E/4, then this one has to be E/4. For this total thing, EMF is E/4, which I have put here. Again, the resistance of voltmeter is V. So this current is almost I, this current is almost same as previous I. Now very small current will be flowing through voltmeter. Now what will voltmeter read? Voltmeter will be reading the current into the resistance. I mean, we will design it in that way, right? So when we write loop equation, plus E/4 minus I into R/4 minus I into V minus E/4 is equal to 0. Now E equal to IR we have seen in the first figure, so I can say the net is going to be 0. So from here I into V is minus E/4 minus E/4. So the meaning is, I assumed, according to my assumption, this is higher potential, this is lower potential, but what I am getting this is lower potential and this is higher potential. Now similarly, if I go for the other case, E/4, E is given as 12 in the question, so that is going to be 3. Now in the second case, again I can say both currents will be same, and this is induced EMF is E/4, resistance is R/4, 3E/4, 3R/4, and if this is 3E/4, this has to be 3E/4 because for the total loop it has to be 0, and this resistance of the voltmeter is V I have taken. So when I write the loop equation, plus 3E/4 minus I into 3R/4 minus small I into voltmeter resistance minus 3E/4 equal to 0. So from there I into V is minus 3E/4. So what I assumed voltmeter, if this will be higher potential, if I assumed this part is going to be higher potential, this part is going to be lower potential, but what I got this is going to be higher potential, this is going to be lower potential. If you want to see higher potential and lower potential in a much better way, you can look at the next example. In this next example, you can read the question by yourself, but I can say what is happening. There is a solenoid and there is a time varying current, so magnetic field will be varying with current, so and it is increasing. If the magnetic field is increasing, then the induced electric field will try to push the current in this loop. If there are no voltmeters, then there is a loop here like this, right? 50 ohm and 50 ohm. Remaining all are resistance aspects, you can assume. So there is a loop like this. There is a loop like this. If there is magnetic field is increasing, then induced electric field will try to push the current in this direction, which has been represented here. If there is time varying magnetic field is increasing, assume voltmeters are not there, then the current will be flowing in this loop, right? Flowing in this loop, current will be flowing in this loop, so that it will be creating some opposition flux. Now all the values you can calculate. The total EMF induced in the loop is going to be 20 microvolt. I am not bothered about that, I am just putting the information given. Now when there were no voltmeters, total EMF induced in this loop is going to be 20 microvolt. So for half loop it is going to be 10 microvolt, and the current in the total one has to be was going to be 20 microampere when you calculate. Now when you put voltmeter, it is almost going to be 20 micro, because voltmeter resistance is very high and very less current will be passing through it. Very less current will be passing through it. So this is almost 20 micro, this is almost 20 micro. Now if I want to find what is the voltmeter reading, I need to see what is I into voltmeter resistance, I1 into voltmeter resistance. So for that I will be writing loop equation. Now again when I take this loop, flux enclosed through that loop is 0. Now if you want to visualize that loop in 3D, like there is one wire like this and there is one more wire like this. Now that loop is totally outside the board. Magnetic field is here, right? But the loop is here. So what is the flux enclosed through the loop? It is 0. So total EMF has to be 0. That can happen how? If this is 10 microvolt, then this has to be 10 microvolt. The total EMF induced in this wire is 10 microvolt, which I have put here. So again when I write loop equation, plus 10 minus I into R minus I into R minus 10, right? Plus 10 minus I into R is going to be 10 in magnitude. So minus I1 V1, which is current in voltmeter into resistance of voltmeter, minus EMF, this EMF, right, is equal to 0. From there I1 V1 is equal to minus 10 volt. What does that mean? I assumed this is higher potential, this is lower potential, which is how I made the connections also. So if it turned out to be positive, if it was positive, then it would have shown me positive reading. Now it is negative, so what will happen? I assumed this higher potential, this lower potential, but it turned out to be this is lower potential, this higher potential. So it will show negative reading to me, it will show minus 10 microvolt. If my assumption was correct, then it would have shown positive value. So in the next case, if you take the second loop, I can draw the same thing, and when I write the loop equation, I will be getting minus 10 microvolt. Now what I assumed this has higher potential, this has lower potential. This has higher potential, this is because current is going in this direction, right? So I assumed, according to my loop equation, I assumed this has higher potential, this has lower potential, but what I got negative value. I assumed this has higher, this has lower, because current is going in this direction. But what I got negative. The meaning is it is the other way. So this is going to be negative and this is going to be positive. I assumed this is positive and this is negative, but I got the other answer. The meaning is this is going to be positive, this is going to be negative. So voltmeter will be finding correct value, because this is positive, this is negative, right? So it will be showing plus 10 microvolt. Okay, then we will be going with this self-induction. So self-induction, how you will be finding self-inductance? You will be passing the current through that loop and you will be finding the flux through the same loop, and that flux will be proportional to the current. That constant is going to be self-inductance, right? So if you want to find the EMF, then it is rate of change of flux, L di by dt and stuff. If there is one loop, it is that much. If there are n loops, you need to multiply with n and stuff. So the first question is find the inductance of solenoid neglecting the edge effects. So if there is a solenoid, what you need to do, you need to pass current through it. So if you pass current I, then what will be the magnetic field inside it? Mu naught Ni. So what is the flux through one loop? It is mu naught Ni into A. So how many such loops are there? If n is number of turns per unit length, if the total length is L, then total number of turns are going to be number of turns per unit length into total length available. So this is the flux, this is the magnetic field, this is the flux through one loop, this is the total flux, magnetic field, area, this is the flux through one loop, these are the total number of loops, so this is the total flux. So which you can write as this much, A into L is volume, so you can say flux is equal to something into I, that something is going to be self-inductance. Now the other thing is, so energy half Li square, and you need to show energy per unit volume is going to be B square by 2 mu. So for a self-inductant, for a solenoid, when I do that, half Li square by volume, L just now I got, if I substitute and when I do volume, volume and volume will get cancelled. I can see it like mu Ni by whole square by 2 mu. Now what is this? This is a magnetic field in the solenoid. So what we got here, magnetic energy stored per unit volume. Magnetic energy stored per unit volume is B square by 2 mu, right? Which we did for solenoid, but it is valid at every point. Now if you look at the next question, a long coaxial cable carries a current I. The current flows down surface of inner cylinder, and it is going like this, and it is coming from the outer surface. So what you can do, if you take ampere and loop, you can find what is the magnetic field there. But what they are asking, if you find the magnetic, that magnetic field is easy to find. It is mu naught I by 2 pi r. I am not going to do it, which you can do. You can take ampere and loop, and you can find what is the magnetic field at a distance r. Now if I want to find the magnetic energy for a length L, that is through this volume, whatever volume from here to here. So what I need to do, I need to take some element where the magnetic field is almost uniform. So I am taking that cylindrical element here, and I need to find what is the energy stored in that element. How to find the energy stored in that element? B square by 2 mu naught is the energy stored per unit volume into that much volume. So B square by 2 mu naught into volume of that thing. Volume of that thing is this area into this thickness. This thickness is L, and this area is 2 pi r into dr. 2 pi r into dr. So B square by 2 mu naught into area into length will give me volume, right? So this is the energy stored in whatever that shaded thing. Now if I want to find total energy stored there, what I can do, I can integrate it. When I integrate it, I will be getting this result. So I can look at the result like half L I square. So sometimes it is easy to find self-inductance using half L I square, sometimes by passing a current and finding the flux through it and looking at it like L into I. Now there is this next question, a square wire frame with side A and a long straight conductor with direct current I naught lie in the same plane. The inductance of the frame is L and the resistance is R. The frame has been rotated through 180 degrees. So initially the frame is like this, thereafter it has rotated 180 degrees and then stopped. Find the amount of electricity, find the amount of charge that has been passed, the distance B between the axis O dash and the straight wire is assumed to be known. So all the distances are given. You need to find by the time you rotate it from here to here how much charge would have flown. Now why the charge is flowing in the first place? Because when you are rotating it, you are moving it in a magnetic field. When you move it in a magnetic field, there can be induced EMF. Now what is the reason here? The reason here initially was because you are moving something in a magnetic field, that is motional EMF. So motional EMF will try to drive the current. If motional EMF tries to drive the current, what will happen? Resistance is there, so it will try to oppose. At the same time there is self-inductance, it will also try to oppose, right? So you must be, I didn't do it, but you must be knowing R and L circuit, how it behaves, right? Now if something tries to drive the current, its resistance will try to oppose it and its self-inductance will try to oppose it. So the equation looks like E minus IR minus L di by dt equal to 0. This is happening because of motional EMF. This is opposition by resistance. This is opposition by self-inductance, right? Now what we need? This EMF is because of rate of change of flux happening through the loop, right? Faraday's law, or the reason here was motional EMF. Now what we need to find? We need to find what is the total charge flown. So total charge flown, I dt. So what I can do is I can multiply all the three terms with dt and I can integrate. Then I dt will give me the charge. This is what I need to find. But what about this? What about this? What was the initial current? 0. What was the final current? This is also 0. So this term is going to be 0. Now what about this? E dt. E dt is nothing but d phi. D phi integration is change in flux. So Q is change in flux by R, resistance. Now how to find the change in flux? Now first of all I need to take the direction properly. So what I will be doing is I will be taking the area direction in this way. So initial flux is, or I need to find only magnitude, right? So anyway, so if I take area direction this way, initial flux is positive. But what is happening to the area direction? Initially area direction was inside, into the plane. So when I rotate it, area direction is going to be out, right? So if area direction is initially this way, area direction is this way initially. So when I rotate this, area direction is going to be this way. So if initially the flux is positive, then finally the flux is going to be negative. If I go with the other way, if I assume initially area direction is this way, initial flux is negative. If initially the area direction is this way, the flux is negative. Finally the flux is positive. So what is the change in flux? positive minus of negative, which is you just have to add both the magnitudes, right? So what I need to do, I need to find the initial flux and I need to find the final flux. Subtraction of them is effectively addition of their magnitudes, right? So how to find the initial flux? I can take some element, I can find the flux through that element and I can integrate it. How to find the flux in the second case? I can take some element, find the flux through that element, I can integrate. Now effectively subtraction of those two flux is nothing but addition of their magnitudes, right? Now in the next question, in the circuit shown, the EMF of the source and its internal resistance and the inductance of superconducting coils are known. Find the currents established in the coils after key is closed. So when you close the key, what will happen? Some currents will try to be going in the inductors, so there will be opposing EMF and stuff, but these two are parallel, so their potential difference has to be same every time. So what I can say? I can say if at any moment if I assume the current is I1 and I2, then L1 di1 by dt must be equal to L2 di2 by dt, because their potential difference has to be same at any point. So I can say like integration. Initially when I1 is 0, I2 was also 0. Now when it is some capital I1, this has to be capital I2. So L1 I1 equal to L2 I2. This I can write at even at any point of time, but I assumed capital I1 and capital I2 are final currents, but I can write that relation for any point of time. But final currents, finally these two will behave like normal wires, right? So then what will be the current flowing? Current flowing will be E by R. So I1 plus I2 must, E by R will be splitting into I1 and I2. So I1 plus I2 is E by R. This I can write only for steady state situation. So these two relations I know, from there I can find the currents in the inductors. The next question, in the circuit shown, switch S is shifted from position 2 to position 1 at t equal to 0, shifted to position 2 from position 1 at t equal to 0, having been in position 1 for a long time. So you need to find, they found the current as a function of time. You need to find what is L1 by R. And yeah, I think you must be aware of this analogy. Now according to this, inductance is something like mass, which is nothing but inertia. Mass is inertia, so inductance is inertia. Mass will try to oppose to change its motion. Inductance will try to oppose to change the flux, right? So mass, whatever is inductance here, it is equivalent to mass. Whatever is momentum is equivalent to flux. Whatever EMF is equivalent to force. So EMF will try to change the flux, force will try to change the momentum, but if there is a finite force, it can't change the momentum immediately. Like if there is a collision happening, we won't consider gravity effect, right? Because that force won't be providing much change in momentum during a small time. The same way, if there is a battery of finite value, then it can't change the flux in the circuit immediately. Anyway, if you go with that logic, so initially the current you can find, I mean when steady state is achieved, current is 20 by R. So what is the flux through this circuit? L1 into 20 by R. Now even when you close this, there is battery or stuff, it can't change the flux immediately. That is the reason, I mean you must be aware of that reason. So flux through the circuit can't change immediately. So initial flux must be same as flux just after closing this. Just before and just after, the flux must be same. So just before, the flux is L1 into I, just after the flux is L1 plus L2. I mean in this one flux is L1 I naught, in this one flux is L2 I naught, right? So this is the initial current here, this is the initial current here just after closing. But at any random time, if I write the loop equation, it will turn out to be this loop equation. So when this is the loop equation, I can write it this way and I can see the figure looks like this. When I know the figure looks like this, the general solution will be of this form, and at t equal to 0, I know the current is I naught, right? Now after a long time, what will be the current? Again 20 by R. So from there I can predict what are the values of A and B, and I can get current as a function of time, Now they have given something in the question, so from there I can compare and I can get these three equations and I can solve them and I can get the answer. So the essence of this question is flux through a loop won't be changing suddenly, just before and just after closing the switch, it has to be same. Now the next question, a superconducting of radius A and inductance L is in uniform magnetic field in the initial position. In the initial position, the plane of the ring is parallel to vector B. In the initial position, the plane of the ring is parallel to vector B. So what is the flux initially? 0, and the current in the ring is equal to 0. Yes, because of this current, I mean there is no current also, so the total flux is 0. The ring is turned to a position perpendicular to vector B. Vector B is this way. So the ring is turned to a position perpendicular to vector B. Find the current in the ring in final position. Find the current in the ring in the final position. Initial flux is 0. Finally, because of magnetic field there is flux, right? So let us see how superconducting material will behave. Now initial flux is 0. Now there is change in flux. If there is change in flux, there will be induced EMF. If you want to find the current, current will be given by magnitude wise 1 by R times of d phi by dt, because this will give you EMF. But in case of superconducting material, resistance is going to be 0. Superconducting material resistance is going to be 0, and in general we will be having only finite currents. So how can that happen when this is becoming 0, and how this can be finite? If this is 0, then it is like 1 by 0 form, right? So how it can happen? If resistance is going to be very small, how the current is going to be finite? It has to be very large, right? That can happen only when change in flux is 0, when it is of 0 by 0 form. I mean, when it is small, when it is 0, almost 0. When this is almost 0, this has to be almost 0. So whenever there is superconducting material, what you can do? You can visualize it like change in flux is going to be 0, which is constant. How much is the flux initially? Initially flux was 0, so at any moment it has to be 0 only. So initially it is 0. Finally, because of the external magnetic field, flux is B into pi r square. Now induced electric field will try to oppose that flux, and it will create exactly the same amount of flux, so that the net has to be same as initial, which is 0. So B into pi r square must be L into I. B into pi r square must be equal to L into I, so that the net flux is going to be 0. B into pi r square equal to L into I. From there you can get I. Now if you know what is the current flowing in it, then you can find the magnetic field at the center, which is mu naught I by 2A. This is the magnetic field at the center because of the current flowing in the loop. Now apart from this magnetic field, there is external magnetic field also. So net magnetic field at the center is going to be this much, which was the question they asked, but this is not so important. What you need to understand is flux will be conserved for a superconducting loop at any time. It has to be same at any time. Now the next question, LC oscillations kind of. The capacitors shown in the circuit are having capacitance the C and 3C, which have potentials 2V0 and 3V0 respectively. So switch S is closed. You need to find what is the maximum current through the inductor and what is the potential difference across C1 and C2. There is no resistance here, so energy must be conserved. So initially it looks like this. This is charged to a potential 2V0, so the charge is plus 2CV0 minus 2CV0 charge, right? Now they are connecting this one, they are connecting inductor, and they are asking what is the maximum current. If the current in the inductor is maximum, if I is maximum, I dash must be 0. If I dash is 0, L into I dash must be 0. If L into I dash is 0, then the potential difference across the inductor has to be 0. If the potential difference across the inductor is 0, I can put it with a wire, right? Anyway, so initially if I calculate the energy in this one is going to be this much, in this one is going to be this much. When I calculate the total energy in the capacitor is going to be this much. Energy in the inductor initially was 0 because it was not connected. Now when I connect it, when I see the maximum current situation, I can replace the inductor with a normal wire, right? So when I replace with a normal wire, I can see if this potential is, if I assume it as 0, then this potential has to be 0 and this potential is V. Now you can see this potential difference is same as this potential difference, and how I can do that? This V minus 0 equal to Q1 by C, V minus 0 equal to Q3 by C. Now why I have taken positive here? Because I know these two plates are isolated. If I join them, the total charge on it must remain same, which is 9 CV0 minus 2 CV0, which must be totally 7 CV0. So charge on this one plus this one has to be 7 CV0. When you solve these two, you will be getting the charges, you will be getting the potential. You can find the energy in this capacitor, energy in this capacitor, total energy in the capacitor is this much. So energy in the inductor half Li square, but I know this total energy, initial and final energy must be same as total initial energy. When I do energy conservation, I will be getting what is the current. Now similarly, if you go with the next question, there are two conducting spheres of radius r are placed at a large distance from each other. They are connected by inductance. Neglect the resistance of the coil. Sphere A is given a charge Q and switch is closed. Then find the charge on sphere B as a function of time. At what time the charge will become Q by 2 and stuff. So what I can do, I know it will be LC oscillation. So at any time when the charge q has flown here, then this charge has to be q minus q. Then the total energy must be same as initial energy. Initial energy is kq square by 2, or self energy of a sphere, right? Hollow sphere, conducting material, so charge will be only on the surface. So this is the initial energy must be equal to final energy, self energy of this one plus self energy of this one, and I neglected the mutual interaction energy because they said it is at a very long distance, plus inductance energy. Now first differentiation has, this is total energy equal to constant, which is initial energy. So if I differentiate it, I will be getting something like this. When I modify it, I will be getting this one. I will be further modifying it because I can, so that I can see the equation much clearly. The same equation I can write it this way, because q double dash or q minus capital Q by 2, which is constant double dash. This is double differentiation. This dot represents first differentiation, this double dot represents double differentiation, right? So now you can see this one like acceleration equal to minus omega square times of displacement form. So it is like SHM form, so there is general solution. What is the general solution? If a equal to minus omega square x, then x will be of the form a sin omega t plus b cos omega t. X will be of the form a sin omega t plus b cos omega t. This is x. Now from here if I differentiate, I will be getting q dash. Now there are two variables I assumed, a and b, so I need two equations. So one equation. I know what is the charge, what is q initially, what was q initially. At t equal to 0, q is 0. What was the current? 0. So both are 0. At t equal to 0, this is 0. So when I substitute 0 in this, q equal to 0 and t equal to 0, this one will be 0, this one will be 1. So from here I can, this is from this equation at t equal to 0. Now when I substitute t equal to 0 here, this is going to be 0, this is going to be 0. From here I can conclude a is 0 and b is minus q by 2. If a is 0 and b is minus q by 2, if I substitute it back, I will be getting q minus q by 2 equal to 0 minus q by 2 cos omega t. So q equal to q by 2 into 1 minus cos omega t. Now if you know this one, you can get the charge on the other sphere also, then remaining you can get easily. So when I see SHM form, I try to get it into this form so that I can write. I use this as generalized solution for my SHM. This is much easy for me compared to the other thing. Now mutual inductance, how to find mutual inductance? You will be passing current through one loop and you will be finding the flux in the other loop. When you see that, it will be like proportional to current. That proportionality constant is called as mutual inductance. Generally, if you pass current in the first loop and find the flux in the second loop, or if you pass the current in the first loop, same current in the first loop and find the flux in the second loop, it is going to be same. That's what reciprocity theorem says, right? Mutual inductance is same no matter if you pass the current in this one and find the flux in the other one, or pass the current in the other one and find the flux through the first one. Right, and you will be exploiting that reciprocity theorem too much. So if you, this is the first question where we do that. There are two circular loops whose centers coincide, and this radius is very small over this radius. So you need to find what is the magnetic flux phi 2 embraced by loop 2. So you are passing current through first one and finding the flux through the second one. That is going to be hard because when you pass a current through this, and if you want to find the flux, okay, if you look at this figure, that's much better. If you pass the current through this and if you want to find the flux through this one, you need to find what is the flux through this one, and you need to find what is the flux through this thing. Where magnetic field we don't know properly. At least here we can find something because we know if we can utilize this like a dipole. So you can find the field because of dipole at some distance, but that you can do only for larger distances. So it is going to be pretty hectic. So what we do is we will try to exploit mutual inductance theorem. What does that say? If you pass the current through the first loop and find the flux through the second loop, or pass the current through the first loop, pass the current through the other loop and find the flux through this loop, it has to be same. So if you pass the current through first one and find the flux through the second one, or pass the current through the second one and find the flux through the first one, both will be same. So what I will be doing is I will be passing the current through the second one and finding the flux through the first one. Why I do that is, as they said area is very small, I can almost say like magnetic field will be uniform, and I know what is the magnetic field due to second loop at the center, which is mu naught I by 2 A2. So this is the magnetic field which I assume almost uniform. So into this area. So what is this? This is the flux through the first loop if I pass the current through the second loop. Now this must be proportional to I, right? So what is the proportionality constant? Yeah, mu naught into pi A1 square by 2 A2. Anyway, that doesn't matter, they asked only flux, fine. Now the next question you can take it as practice for you. Okay, again mutual inductance only, a loop with current I is in the shape of a rectangle, find the magnetic flux through the hatched half plane. You need to find the flux through this half plane. Now you need to know the dimension, so you can just assume like the dimensions are this way, A, B and L. But still it is going to be difficult. So what we are going to do, instead of passing the current through this loop, we will try to pass the current through this loop in the same way what we have done earlier. But how to visualize plane like a loop? I can visualize like it is like an infinite current carrying wire, and it will be making a closed loop at other three borders at infinity. So their effect will be 0 here. Their effect will be 0 here. So instead of passing the current through this one and finding the flux through this one, I will be passing the current through this one and finding the flux through this one. So if I pass a current, then magnetic field will be mu naught I by 2 pi into x. I can find the flux through this one, I can find the total flux. That's the answer, right? I can find the flux through the element and I can integrate, I can find the total flux. So and this is going to be the total flux, and this is going to be the mutual inductance between them, right? Okay, the next question. The mutual inductance of coil 1 with respect to coil 2. So the meaning is, if you pass current through the first coil and if you find the flux through the second one, that proportionality constant. And if you look at last option, the last option says M21. The meaning is, if you pass the current through the, okay, whatever. So yeah, you can go with respect to coil 2. Okay, so you can take one definition as pass the current through first loop and find the flux through second loop. Let me say that is this definition. Let me say M12 says magnetic flux. Okay, I think it's better to the other way. So let me say magnetic flux through the first loop because of the current in the second loop is M12. So if there are two loops, first loop, second loop, if I pass current through second loop and find the flux through the first one, and if I find that proportionality constant, and in this case if I pass the current through first loop and find the flux through the second one, will they be same if I pass the same current? Yes, because mutual inductance will be same, or these two will be same. That is what we say in reciprocity theorem, right? Anyway, so option D I am not going to talk much about. Now mutual inductance will increase when they are brought nearer. Is that? Yes, when you bring them nearer, then the flux, if you pass some current through this, then if you pass some current through this loop, what will happen? There will be magnetic flux, right? So when you bring these two closer, the magnetic flux piercing through this one is going to increase. So when you bring them closer, mutual inductance will increase because flux increases. Now what about B? Depends on current passing through the coils. Mutual inductance doesn't depend on the current, it depends only on the orientation stuff, right? Geometry and orientation. It increases when one of them is rotated about axis. There is no way you can conclude that. Now what we understood here, so when you bring them closer, the flux piercing through the other loop is going to increase, so mutual inductance is going to increase. So if you take some similar coils and if you exactly place one on another, like the next question, we will see what is the relation. So there are two solenoids of same length, but self-inductance is L1 and L2, so you need to find what is their mutual inductance. So self-inductance, how to find self-inductance? Pass current through first loop and find the flux through the first loop. So if I pass current I, then magnetic field is this much area, so this is the flux through one loop, these many loops are there, so this is the flux through the total solenoid. A into L is volume, right? So this is self-inductance of first coil. Similarly, self-inductance of second coil. If I want to find mutual inductance, I need to pass current through first loop, then it will give this much magnetic field. So flux through the second loop I have to find, so I have to take area of second loop, right? So area of second loop, which is same in this case, same as first loop anyway. So mu naught, this magnetic field due to current in the first loop, and this is the area of the second loop. So this is the flux through second loop because of current in the first loop. But this is for only one round. So how many such rounds are there? N2 into L. So this is the mutual inductance. When you get the relation, it is going to be L1 L2 equal to M square, or M equal to root of L1 L2. M became equal to root of L1 L2 when you place it one on another. So in all the other cases it has to be less than root L1 L2. Now there is this question. A small cylindrical magnet, you can see the figure. A small cylindrical magnet is placed at the center of thin coil of radius A containing N turns. The coil is connected to a ballistic galvanometer. The resistance of the circuit is R. After the magnet has been rapidly removed from the coil, a charge q has passed through the galvanometer, find the magnetic moment of the magnet. So what we are doing here, there is a galvanometer, ballistic galvanometer. What it does, it finds how much charge has flown through it. So you have placed some small bar magnet here and you suddenly taken it out. So you can see there will be charge flown through it because you are changing the flux. If there is change in flux, there will be induced EMF. So if there is induced EMF, there will be current flowing. If there is current flowing, it will detect charge, right? So again, when there is EMF, it will try to produce the current, right? So when you write loop equation, it looks like this. This EMF is because of change in flux, and opposition because of resistance, opposition because of self-inductance equal to 0. So I need to find what is the charge. I mean, we have seen similar equation earlier also. So when I integrated this, I will be getting this one as 0 because initially current is 0, finally also current is 0. Now what I need to find? I need to find some other thing. I know this one because this is measured by the galvanometer. So I need to find something which arises somewhere here. So let me see what is delta phi. What is the final flux? Final flux is 0. So I think I need to find initial flux. So the question boils down to finding the initial flux. Now there is a problem with finding the initial flux. You need to find the initial flux as this much. So if you can find initial flux as this much, then you can find the magnetic dipole moment, right? So how to find initial flux as this much? This is the question. Now we can do one thing. Now there is a bar magnet. How I can visualize bar magnet is, I can visualize bar magnet as a small current carrying coil. If there is small current carrying coil, I can visualize it like a bar magnet. But the formula what I know for dipole bar magnet are only far distant when they are not close, right? So I can find field because of this bar magnet or this current carrying loop only when it is little far. So if I want to find the flux enclosed here, I can't find it easily. But I have a trick here. If the current is flowing through this loop, then what will happen? Okay, let me say this is the loop. If current is flowing through this loop, there will be some flux through this loop, and the same flux will be emerging out, right? So, or else I can say the field lines have to be closer. So whatever field lines emerging out from this, they will be going here, right? They will be going into. So whatever flux happens through this black color, whatever flux will be inside this black color, how many field lines will be coming from this entire black color thing will be same as the field lines going into the board. How many will be coming out from here will be the same as going into the board. The other way of saying it is, if I want to find the flux through this one, instead of this I can find what is the flux through this region, because finding flux through this region is going to be easy. Further what I will be doing, I will be taking some element, I will be finding the flux through that element. If I want to find the flux through that element, what I need to do? Magnetic field mu naught by 4 pi into p by r cube, like kp by r cube form, right? Into that area is 2 pi r dr. This is for one loop, one such loop, right? Now how many such loops are there? N such loops are there. So anyway, so you can find it, which will turn out to be n into mu naught p by 2 times of A. But that is the integration which is going to be so complicated, but we could have avoided that. How we could have avoided that? I could have avoided that. How I could have avoided that? I need to find the flux through this ring by passing the current in this one. I mean, there is a bar magnet. I visualize the bar magnet as some current carrying coil. So if current is I and the area is pi into small r square, or this radius is r, then what is my aim? My aim is to find the flux through this loop. But what we know, mutual inductance theorem, you pass the current through this one and find the flux through this one, or pass the current through this one and find the flux through this one, both have to be same, right? So I will pass the same current through this one and I will try to find the flux here. So magnetic field here is mu naught I by 2a into area, this one is pi r square. For one loop it is this much, so there are n such loops, so it is n times of that. But what is I into pi r square? I into pi r square is dipole moment of that first one, right? So this is the same thing we got in a much easier way. We got this one much easier way by using mutual inductance. If we don't use mutual inductance, we will be getting using some lengthy way, right. So you can exploit mutual inductance, right. Thank you.